we have Daniel Litt from the University of Toronto, who's going to be speaking about p-Curvature and non-Abelian cohomology.
Thanks so much for the introduction. It's nice to be here. So I know some of you have seen a talk by me on p-Curvature and non-Abelian cohomology before. If you saw it in this room, this is a different talk. Okay, so let me start by fixing a situation. So X to S will be a smooth proper morphism, a smooth projective morphism, where S is smooth over a ring R inside of C, and R will be a finitely generated Z algebra. So one of the themes of algebraic or arithmetic geometry over the last 70 years or so has been that there are some connections between the arithmetic of a situation like this and its topology. So my goal of this talk is to explain some kind of non-Abelian instance of that story. So I think most connections between arithmetic and topology have typically been mediated by cohomology. So cohomology has various realizations, some of them arithmetic, some of them more topological. And I want to talk about some kind of connections passing through non-Abelian cohomology. Okay, but let me start by just recalling the Abelian setting. So in this case, the topology of pi is captured by a representation of the fundamental group of S. So topology, one studies the following representation of pi1 of SC and Litt phi. Let me fix a base point. Okay. On the cohomology of fiber of this map. Let's say with complex coefficients. So this captures some of the topology of this map. And it has some extra structure which I didn't write down, which will become important for us. Well, we can equivalently think of it as a local system on S or SC, and inside of here, there's a Z lattice. Inside of this group, there's a Z lattice that's preserved by pi1. Okay. So this is a purely topological invariant of this map. It only sees the analytification of the complex points. So we can compute the same object using differential geometry. So namely, this local system can be computed using the de Rham complex, using differential forms. So one can take Ri, pi lower star of the analytic de Rham complex, for example. And this is equipped with a connection, the Gauss-Manin connection, which captures the monodromy of this representation. So let me just write that down. So this you can recover by taking the local system we saw before, tensoring it with OS, and then taking the connection, which is the identity tensor D. So this is a flat vector bundle. But writing it this way tells you it has some extra structure. So this is the hypercohomology of some complex. So in particular, it comes with a filtration by degree. And then there's also a polarization. So this carries a polarizable variation of Hodge structure we saw in Ben's talk. Let me just record on another board the properties of this data so that I can use them later. So here, this is a flat vector bundle, which just means that it's a pair E nabla, where nabla goes from E to E tensor omega 1s and satisfies two conditions. So one, it satisfies the Leibniz rule, which is that it's the product rule from first year calculus. And two, it's flat, which means that the adjoint map from the tangent sheaf to the endomorphisms of E is a map of Lie algebras. This is an associative algebra, so in particular, it's a Lie algebra. This is a Lie algebra given by taking commutator vector fields. Okay, and then finally, one can do the exact same thing in algebraic geometry or arithmetic. It's replacing analytic differential forms or smooth differential forms with algebraic ones. So I'll just write Ri, I lower star, x over s. And then Katz told us how to endow this naturally with the structure of an algebraic flat bundle with an algebraic flat connection. So this is a algebraic flat. And it has some extra structure. So here I've recorded some structure. I'll just say the words and say what they mean later. So this carries, for example, in characteristic P, a conjugate filtration. There's some other new interesting filtration, which has some interesting behavior with respect to the Gauss-Manin connection that we'll see later. Okay, so the basic question when you write down all these structures is, how are these structures related? And in particular, how is the arithmetic of this differential equation reflected by the topology of this map, by the representation we first saw? Okay, and in fact, in full generality, there's a conjectural answer to that kind of question for arbitrary flat bundles due to Grothendieck and Katz. So to explain what that is, I need to describe another piece of data on flat bundles, and then I'll tell you what Grothendieck and Katz conjectured about the relationship between the monodromy representation of a flat bundle and its arithmetic. Okay, so in characteristic P, this tangent sheaf here is not just a Lie algebra, it's a p-Lie algebra. Meaning if you take a vector field, you can iterate it p times, that gives you a new vector field, a new derivation. This just comes from the fact, like the divisibility properties of binomial coefficients with the p on top. So that lets us make the following definition. In characteristic P, there's a map called the p-Curvature, which goes from the Frobenius pullback of the tangent sheaf of S to now the O-linear endomorphisms of E. And it's just induced by the following thing. You take a vector field and send it to nabla v to the p minus nabla v to the p. So it measures the failure of this map to be a map of p-Lie algebras. Okay. And so the conjectural answer to this question in general is the following. So this conjecture is due to Grothendieck and Katz. It's called the p-Curvature conjecture. I think 1968 is the right? Awesome. 69. 69. Okay. 69 there. And it's the following. So given an arbitrary flat bundle, I suppose E nabla is a flat vector bundle on S, our smooth variety over a finitely generated C algebra, then E nabla admits a full set of algebraic solutions. So what that means is that it's at least over C, it's trivialized on a finite hull cover of S. If and only if the following arithmetic condition is satisfied, namely these p-curvature maps of E nabla mod P are identically zero for all but finitely many primes P.
So S is replaced by an open set.
S is, I think the way I've written it, it's okay either way because I passed it to C here. So I'm just saying it's finite monodromy, so you pass to a cover, you pass to the cover given by the monodromy, and then it's trivial.
It's not a finite hull cover of all of S.
Oh, sorry, SC, sorry, SC. That's C. I think it's okay. Sorry. Thank you. Okay. So this conjecture is widely open, but in this case, it's a theorem of Katz. I think published in 1972. So I want to write it in two different ways. So first of all, suppose that for this particular bundle, Ri pi over star with its Gauss-Manin connection mod p. So this is 0, even for infinitely many p. So then we have the following topological consequence. Then the action of pi1 of s on the cohomology of a fiber factors through a finite. Let me put a z here. Factors through this is the first theorem, and then it's an immediate corollary from the fact that Gauss-Manin connections have regular singularities, that the p-curvature conjecture is true for these flat bundles. P-curvature conjecture is true for Gauss-Manin connections.
In fact, if that given the data, you can, that p large enough is explicit.
So Katz only needs infinitely many p, actually. So it's
So but if you're given the data, it's fixed, then surely that
like, can I find a specific p that guarantees?
once p is
Yeah, I don't see how to extract a concrete bound like that. And maybe let me just say, in the conjecture, it's definitely not true that infinitely many p is enough. At least density. Okay.
General, so,
Yeah. Well, density 1, maybe we don't know. Density 1 is enough.
density one.
Probably is enough. Yeah. But yeah, any density less than 1 with their counterexamples. Okay. And so let me just remark, I think this is like the strongest, maybe the strongest evidence still for the p-curvature conjecture, but there's been a huge amount of beautiful work on it by many people in this room. So in particular, so there's work by Chudnovsky, Bosch and Andre on the case of flat vector bundles with solvable p-curvature, or sorry, with solvable monodromy. And this is in the spirit of Siegel's work on G functions, which we'll see some kind of other descendants of later in this workshop. I think what got me interested in the subject is work by Shankar and collaborators, Shankar and Shankar Patel Wang, who studied, so Shankar in particular studied the behavior of the p-curvature conjecture under degenerations. And then what I'm going to talk about for the rest of the talk, so the kind of non-Abelian setting, I think was first studied by Kissen and his students, Menzies, Papaionou. And then there's also beautiful work by Inu and collaborators, which I don't think I have time to summarize. Okay, so what I'd like to do for the rest of the talk is explain what happens when you replace some of these objects by their non-Abelian analogues, by which I mean spaces of representations of pi1 or spaces of flat bundles. Okay. Before I do that, are there any questions about this setup? Okay, great. So maybe let me remark, Katz's proof of this theorem, which I'll kind of give an overview of later in the talk, uses all this extra structure. And so to formulate an analog, one needs to find sort of analogues of this extra structure on cohomology in a non-Abelian setting. And that's really, at least in my view, the main purpose of this talk. Okay. So yeah, let's do the non-Abelian setting. Non-Abelian setting. So what replaces the monodromy action of pi1 of the base on the cohomology of the fiber? Well, the first thing one can do is the following. So a smooth proper map or smooth projective map over the complex numbers is in particular a fiber bundle. And so this gives us an outer action of pi1 of the base on pi1 of the general feature of fiber bundles. Since this is only outer, I don't have the base point here.
Well, if the base is small,
I'm sorry?
we need that the base is, there's no pi 2.
So I claim this action always exists.
Also,
I agree it's not totally obvious if there's pi 2. But yeah, there's a map from S to B diff that gives you some.
So the big S is a little s.
This is a little less. The fiber has. Okay. So this is not a linear enough object to study. So, but what such an outer representation gives you is an action of this group on the space of conjugacy classes of representations of this group. So what this yields is an action of pi1 of the base on what I'll call embedding of the fiber. And what this is the space of representations of pi1 of the fiber to GLR, group GLR of the conjugation. So this is the non-Abelian version of the monodromy representation we saw. Okay. So we'd like to understand how is the topology, whatever aspect of the topology of this map that's captured by this dynamical system reflected by the geometry of some other invariants, which should be analogues of analytic and algebraic around cohomology. Okay, so what is geometry? It goes instead of the around cohomology with its Gauss-Manin connection. Well, the Riemann-Hilbert correspondence tells us what to do here. A representation of the fundamental group of a complex manifold is the same as a holomorphic flat bundle. So if we'd like to understand this in a geometric way, we should, instead of looking at the moduli space of representations, look at the moduli space of flat bundles on the fibers. So let's take M de Rham of X over S. So this is now a family over S. This is the moduli of flat vector bundles on X over S. Great. So here I've made a space for you. You should think of this as being analogous to the vector bundle underlying the round cohomology of the fibers of this map. So what is the analog of the Gauss-Manin connection? And again, the Riemann-Hilbert correspondence tells us what to do. So we can analytically describe this as follows. Take embedding of a fiber, multiply by the universal cover of S. Here, this is the universal cover. And then mod out by the diagonal action of pi1 of S. So here, pi1x on the Betti moduli space as I described here, and on S tilde by depth transformations. This obviously is S. And well, this is a product, so this quotient is locally a product, and in particular, it carries a foliation. But this carries a foliation, and I'm lying slightly, and I'll explain in what way now, which I'll call F isomonodromy. Which is a descent of the tangent bundle of S tilde. Okay. So why am I lying? Well, this is really some. It's not smooth. It doesn't make sense to talk about foliations. It's not a scheme. It's a singular stack. What I really mean to say is that this is a crystal over S. That was explained by Simpson. Okay, but if you'd like, this is true if you restrict to the smooth level of the good modeling space. Okay, so this is some differential equation equipped to this associated to the story, and the leaves of this foliation capture this action. So let me just tell you what the leaves are. So the leaves, and this follows from the analytic description I've given here, are families of flat bundles whose monodromy representation is locally constant. Okay, so I've given you some analytic construction of some kind of differential equation which captures this non-Abelian invariant of topology. So what I want to explain now is that it has some arithmetic content. So again, we can take this m de Rham x over s, and well, it's you can just write down the same moduli problem algebraically. And when one does so, it's a theorem that there's a natural descent of f isomonodromy to an algebraic foliation on this thing, which I really mean again that this is this descends to a crystal on S with algebraic foliation. I'll again just write this f isomonodromy. So over C, the fact that this foliation is algebraic is, I think, again due to Simpson. I'm not sure where it was first written down in the algebraic setting, but it's in a paper of mine with Josh. Okay. So again, the question becomes exactly the same. Well, how are these structures related? So in particular, can you understand something about the dynamics of this action of pi1 of the base on representations of pi1 of the fibers in terms of the arithmetic of this foliation? And again, there's a conjecture about this in total generality and for all foliations. No one can generalize it without trouble to these kinds of crystals of what I'm discussing. So let me tell you what the conjecture is. So I think this conjecture is originally due to Echodol, Shepard-Barron, Taylor. I think it first appeared in printing work of Bosch, who I think proved first significant results about it. And it's the following, and I'll state it for foliations. If you want to know how to formulate it for crystals, ask me after the talk. So suppose S is smooth over our subfield of C, which is a finitely generated Z algebra. And suppose F is a foliation. So what do I mean by that? I mean, it's a subbundle which is closed under the Lie bracket. This is again a sheaf of Lie algebras, and I want this to be a subbundle which is closed under the Lie bracket. So the theory of Taylor series tells you that's what you need over the complex numbers to write down analytic local leaps of this foliation, analytic local solutions to the corresponding differential equation. But in characteristic P, you can ask more. You can ask the analog of this question, which is it not just a subsheaf of Lie algebras, is it a subsheaf of P Lie algebras? And then the conjecture is as follows. So all complex analytic leads of F are algebraic, meaning algebraic subvarieties of S, if and only if F mod P is closed under P powers. For almost all times P. So this is the conjecture. It's a generalization of the Grothendieck-Katz p-curvature conjecture, because if you're given a flat bundle, its total space is equipped with a foliation, and this condition becomes exactly the same as the vanishing of the p-curvature from B. Are there any questions about this statement? So let me tell you the main theorems of the talk. So let me leave Katz's theorem up. I'll write down some parallel theorems in this non-Abelian setting. So theorem 1. This is point work with Josh Lam, like everything in the talk. So suppose, maybe I should say, the forward direction of this conjecture is easy. So the content is, you given a foliation, you assume it's p closed. You want to show something about the leaps being algebraic. So let me first state a theorem which is analogous to this. So this theorem said that if p-curvature vanishes, then the action of pi1 on the integral singular cohomology passes through a finite group. And we have an exact analog of that theorem.
So can I ask,
Please.
is this conjecture you wrote here?
Yeah.
Does that imply that p-curvature conjecture would look at a total space or
Yes,
something?
yeah. So you take S to be the total space of your flat vector bundle and F to be the corresponding relation, or on the frame bundle, whatever. Okay. Okay, so suppose this isomonodromy foliation. So this algebraic differential equation here, mod P is closed under P powers, a subsheaf of P Lie algebras for infinitely many prime is P. Then the action of pi1 of the base on integer points of the Betty moduli space of the fiber factors through a finite.
That really, can you go to an extension of a number field there?
Yeah, you can replace Z with any ring of integers of a number field, but the group might change. Which is sort of at least a priori it might change. That's sort of why we don't immediately get this and all these corollary.
Can you repeat the remark? I'm sorry.
Yeah, so the statement, I'll write this down later too, but the statement was that the theorem is true is if you replace Z with the ring of integers of the number field, but we don't know how to bound the group independent of the number field.
Ah, okay.
Okay, so in particular, I mean, for many of the varieties you know and love, like curves, this there are many Z points. There's many representations of pi1 into GLRC whose traces lie in the integers. But we don't know in general that this is a non-empty set. I mean, in general, I think and aside from the trivial representation, maybe it could be empty. Okay, nonetheless, so we can't quite prove the Echodol-Taylor conjecture in this setting, but we can almost do so. So let me say what we can prove, and it's now not a formal consequence of theorem 1 because we don't really know that there are a lot of Z points. So what we can show is that this Echodol-Taylor conjecture, the non-Abelian version of the p-curvature conjecture, is true for the component of M Duran containing the trivial representation. The component containing the trivial representation. Trivial R-dimension representation.
So here's the family was any?
Any smooth proper morphism. Yeah. Yeah, I should say, I mean, I think we were a little lazy. I think you could probably do this if you put a SEC advisor. There are a few additional analytic complications, but I think they can be overcome probably.
What do you mean by the conjectural holding for this like space MDR?
Yeah, so what I mean is that if you're given X to S and the hypothesis is satisfied for this component of M Duran, meaning the isomonodromy foliation is closed under P powers, then all the leaves in that component are.
Okay, so this is for like the isomonodromy for MDR. This is another component of MDR.
Yeah, that's right. Yeah. I can erase the definition of a flat bundle now. So let me make a couple remarks about these results. Remark. Okay, so theorem 1 is true with Z replaced by OK, so the ring of integers, the number field. And then, okay, so theorem 2, we really prove more. So theorem 2 holds for any component with z bar point. And so we note this for the component containing the trivial representation, because the trivial representation gives you a z bar point. But for example, we know this in other cases, so we know that this holds for all components if R is 2. So if you put a 2 there, this Echodol-Taylor conjecture is just true for these moduli spaces. This isn't totally obvious. This follows from work of Corlett-Simpson on non-Abelian Hodge theory. Yeah.
By z bar point, you mean for embedding?
Yes. Sorry. Yeah. Any component where embedding is. Yeah. Sorry. Where embedding has a z bar point. Thank you. Yeah. Any other questions?
So you can't handle OKS, right?
We definitely can. If we could handle OKS, we would do it. Yeah. That's right. Yeah, we're working on it, but I think one needs some new ideas.
OKS means finite.
Yeah, like okay, invert. Any other questions about this? Okay, so for the rest of the talk, I want to tell you about the idea of the proof, so I can say what it is in one line, and then I'll expand on it.
Maybe I have a.
Oh, yes.
So when you say conjecture is true, so that means here's the conjecture is that you have vanishing. So
Yeah.
I mean, on these components, the
Yeah.
assumption is fulfilled.
Yeah, so
that's
suppose,
true,
yeah, so
that's,
suppose the p-Curvature of the isomonodromy foliation just on that component.
On that component.
Then,
Okay.
yeah, then all the leaves on that is left for algebra.
You don't need just a point somewhere else.
That's right. Yeah, in this, I mean, in this remark, you have to worry about that kind of thing. That's why I left it with the remark, but put that out.
Proven all leaves algebraic, is it the same as finite model?
Yes. It's not totally obvious, but again, follows from the theory of regular singularities, as I'm sure you know well. Yeah.
And you need density 1, or you need infinitely many primes.
So in this theorem, we need infinitely many primes, just like in Katz's theorem. Of course, in the Echodol-Taylor conjecture, you surely need at least density 1, or maybe almost.
But in your proof of theorem 2, you also need.
Yeah, and the proof of theorem 2, you also only need an set of primes. Okay, so let me say in one word what the idea of the proof is, and then we'll spend some time talking about how to execute that idea. So the proof is to copy the proof of Katz's theorem. Okay, and of course, there are some challenges that have to be overcome there. So I told you a bunch of structures on these various realizations of the cohomology of an algebraic variety, which I guess I've now erased. So what one needs to do is figure out analogues of all the structures in this. So let me begin to explain that now. Section 3 of the talk, which is structures on non-Abelian. Cohomology. So I want to start by giving a kind of very quick gloss of Katz's proof of his theorem, so you can see kind of what structures one needs to define in the non-Abelian setting. So I would divide it into 3 parts. So here's Katz's proof, and please feel free to correct me if I say something wrong or try to oversimplify something. Okay, so the first step I would say is arithmetic. And so one way to gloss it is as follows. So Katz is trying to show that if the p-curvature of the Gauss-Manin mod p vanishes for infinitely many p, then some topological conclusion is satisfied, but we have to connect p-curvature to something we can understand better. So in particular, the first step kind of tells you how it's connected to the behavior of the Gauss-Manin connection with respect to the Hodge filtration. So here's the conclusion of that step is that if Cp of the Gauss-Manin connection, p-curvature on p 0 for infinitely many p, then the Gauss-Manin connection preserves the Hodge filtration. And I mean, Katz proves much more than this. What Katz really proves is something called Katz's formula, which is that I'll write down a formula and then try to express what it means. So the pullback through Frobenius of the associated graded with respect to the Hodge filtration of the Gauss-Manin connection can be identified with the associated graded with respect to the conjugate filtration of the p-curvature. So here, I mean, these are maps whose sources and targets are not a priori identified. So one needs to identify them using Cartier theory, but I'm going to suppress that. But what you should think that this is saying is that one can read off the obstruction to the Gauss-Manin connection preserving the Hodge filtration in some way from the p-curvature. This is true with no p-curvature vanishing assumption. I mean, there is some liftability assumption, but I'm going to take this first. Okay, so this is some arithmetic statement. So step 2, can people see if I write down here or is it blocked by the, okay, it's blocked. All right, so let me erase. I don't want to erase this. It's this. Oh, thank you. Or destroy anything. So step 2 is geometry. And it's really sort of a consequence of the Hodge index theorem. Just that if the Gauss-Manin connection preserves the Hodge filtration, so if the consequence of this part 1 is satisfied, so then the action of pi1 of the base of our family on the cohomology of the fiber is unitary. This is something that the Hodge index theorem is something that captures the compatibility between the polarization on the spectral space and the Hodge filtration. If the monodromy preserves the Hodge filtration, then it preserves a definite inner product on each piece, and one can change the signs to make it actually unitary. Okay, and now step 3, I'll call this topology. So now we have some representation from pi1 of S into GL of the cohomology of the fiber. And we just said it factors through the unitary group, but it also factors through the automorphisms of the integral cohomology. This group, the unitary group, is compact, and this group is discrete, and a discrete compact set is finite. Okay, so modulo the details of each step of this argument, we've proven this theorem of Katz. We've produced a finite group that this representation factors through. And I think, I mean, among the many innovation in Katz's article, I think the bulk of it is spent proving this. All right. So now I want to explain how one executes this strategy in this setting. Before I do so, are there any questions? Okay, so what do we have to do? We have to find some analog of the Hodge filtration and show that it is preserved under our hypotheses that the p-curvature of the isomonodromy foliation vanishes. Then we have to find some analog of the Hodge index theorem, and we have to put it together with some kind of integral. So let me do that. This is now going to be proof of theorem 1. So let me recall for you that what we want to show is that if this arithmetic condition is satisfied, if the isomonodromy foliation mod p is built under p powers, then the action of pi1 on this set of integral representations factors through a finite group. If I can, I'll say a little bit about theorem 2, which doesn't require too much more. Okay. So the first step will be arithmetic. And what it is it will be a non-Abelian version of Katz's formula. I'm not going to write down the formula, but I'll tell you the consequence analogous to this. Okay, so first I have to tell you what is the Hodge filtration in this setting. That was answered earlier by Simpson. Maybe deleted. I'm not sure about the history here, so I think someone can tell me. If someone wants to tell me, you should feel free. Okay, so what this is the so-called Hodge moduli space, which is a family over the affine line over S, which is the moduli space of lambda connections. So let me tell you what that is. So this is the moduli of lambda connections, E nabla lambda. And what is a lambda connection? So here nabla is again a map from E to E tensor omega, such that nabla of a function times a section is f nabla s plus lambda s tensor dx. Lambda is some function. So let's think about this. So if lambda is 0, this is just saying that this nabla is an Olin. Oh, sorry, I'm missing a condition. And nabla composed with nabla is 0. So this is analogous to flatness. Okay, so if nabla is 0, what is this saying? It's saying that this is an O-linear map, and this tells you you have a Higgs field. If nab lambda is 1, this is saying you are a flat connection. So maybe let me just verbally say a word about why this is analogous to the Hodge filtration. So filtration on a vector space, okay, with some adjectives, is the same as a GM equivariant vector bundle on A1. This has an action of GM by scaling nabla and lambda. And so it's a GM equivariant stack over A1, whose fiber is M-Durand. We're supposed to think that's something like a filtration on M-Durand. Okay. So this is the Hodge filtration. And what we would like is to understand what it means for the Gauss-Manin connection to preserve the Hodge filtration. Okay. So let's make an observation about the geometry of this space. Well, I said part of it, so M Hodge X over S R lambda, so the fiber over some point lambda of A1 has the following interpretation. If lambda is not 0, this is just M-Durand. And if lambda is 0, this is what people call M-Dolbeau, so the moduli of Higgs bundle. Okay, but what this tells us is that each fiber of this map is equipped with a foliation. Well, each of these fibers is isomorphic to M-Durand, so it has the isomonodromy foliation. And let me make the following definition. We say F isomonodromy preserves the Hodge filtration I'm defining this phrase preserves the Hodge filtration. If it extends to the central fiber M below, which is the fiber over 0. So we have a foliation away from 0, and I want to know, does it extend across the central fiber? If you think about filtered vector spaces, this is translated into the language of J equivariant vector bundles on A1. It's really the same thing. Okay. And then, so theorem A is the analog of Katz's theorem here. So if this isomonodromy foliation is closed under p powers, or infinitely many times p, then F isomonodromy preserves the Hodge filtration. This is, I would argue, the precise non-Abelian analog of this statement here. Let me just remark that it's a consequence of some theorem A prime, which I won't write on the board, which is a non-Abelian version of Katz's formula. So I'll just say a word about what that looks like. So there's some other kind of non-Abelian filtration on M, which is analogous to the conjugate filtration, and then some objects on the central fiber of that. That's the same up to Frobenius twist as the obstruction to extending this foliation across the 0 fiber of M Hodge. Okay. So maybe before I move on to step 2 of the proof, let me just make a remark about this theorem. So about the history of this theorem. Mark, so this situation was studied by Menzies and Papayano in their theses. So we certainly rely on their ideas, and in particular, so Menzies proved theorem A under the assumption that there's some Frobenius lift on X over S. This is kind of too strong an assumption to use in practice, but certainly the idea of the argument was very important to us. And in particular, let me remark, so the proof of theorem A relies heavily on August Vologodsky's work on non-Abelian Hodge theory and characters of P. Okay, so that's step 1 done. So we've said, here, sorry, let me erase this off. So we've used our hypothesis that there's some arithmetic condition satisfied by the isomonodromy foliation. It's closed under p powers and reduced mod p for infinitely many p. And now we're reduced to a question really in topology, or really, I guess, in complex geometry. If we're in some situation where the isomonodromy foliation preserves the Hodge filtration, what can we say? So can we prove theorem 1 and theorem 2 in that? So now we need to find an analog of the Hodge index theorem, figure out what it means for this action here to be unitary. So this is kind of the geometric step. So this is, we're now doing analysis. Theorem B. And I think this is at least some kind of analog of the Hodge index theorem. Consequence of the Hodge index theorem. So if at isomonodromy observes the Hodge filtration, then, okay, and it turns out there's sort of actually two analogues of the Hodge index theorem here, although they're both consequences of something of the same thing. So the first statement is that the orbits of I1 on the Betty moduli space on the corresponding complex analytic space have compact closure. I mean, you fix a point here, you take its orbit, that's some subset of this space, and you take its closure in the analytic topology, and that closure is a compact subset in the analytic topology. And then step 2 is on the smooth locus, by which I mean this is non-reduced on the smooth locus, the reduced subscheme. This action preserves a counter. And for those of you who are experts, both of these statements are consequences of the fact that the energy functional on the space is preserved by isomonodromic deformation with this hypothesis.
Maybe we have zero smooth locus, you mean the reduced?
Yeah, on the reduced smooth locus. Yeah. Okay. So let me almost finish the proof of theorem 1 here, and then say a little bit about what's missing in theorem 2.
You still need the Z part to have some variety.
I'm sorry?
I mean,
Oh, yeah, I haven't done that yet.
Oh, so.
That's the next step. Yeah. So step 3. So let me prove a slightly weaker version of theorem 1. So step 3. Now this is so step 3. This is the corollary of 1 and 2. So the orbit of any Z point of the Betty moduli space is finite. Whatever any Z point here under that I want the base. So here, this corollary I'm about to prove is a bit weaker than this theorem. It's just saying that for any point, the action on the orbit of that point factors through a finite group. In this theorem, I'm saying there's a uniform finite group that works for all points, but that's a sort of general fact from arithmetic dynamics. There's no real additional input to deduce that from this statement. Okay, corollary. So what's the proof? Well, the orbit is discrete because it lives inside of the Z points of this affine variety, which is a discrete set, and compact by 2. And it's finite. So that is the content of the proof of theorem 1. So in the remaining few minutes, I just want to say what additional work one needs to do to get theorem 2.
When you go to a number field, you have the other embeddings built into this naturally.
Yeah, so the Galois action commutes with the pi1x action, I guess. Yeah, and that, oh yeah, maybe you're asking about how to prove this. Yeah, somehow you handle all conjugates simultaneously. Okay, so now let me say what goes into proof of theorem 2. Okay, actually, before I do that, let me just briefly remark, I think there's some experts on p-adic non-Abelian Hodge theory in the room. I think it's kind of likely that this non-Abelian version of Katz's formula is part of the package of prismatic F gauges. So if someone can explain that to me, I would be kind of curious to understand that viewpoint on this.
Can you repeat the sentence?
I think it's
Package what?
I think theorem A has real geometric content, like we really need Opus-Woligodsky to prove it. But I think the underlying non-Abelian version of Katz's formula is probably part of the package of prismatic F gauges, or maybe it should follow from the geometry of the Durand stack. And so I would be interested in understanding if someone in the audience immediately knows how to prove a non-Abelian version of Katz's formula from that point of view. I mean, I can tell you what the formula is, and then maybe you'll know how to do it. Okay, so let me say what one needs to prove theorem 2. So there's a little bit of arithmetic one needs to do to get to a situation like this, but just to simplify things to tell you the idea, let me just assume that Mbedi XS are 0, so this thing, let me assume it has a smooth z point. So one can use ideas I learned from Ellen and Young to go from the existence of a z-bar point to a smooth z-bar point, and this is what we really use, but for this argument, let me just assume that we're already given a smooth z point. So by theorem 1, let me call the point rho. By theorem 1, the action of pi1s on rho that is through finite groups, so this orbit is finite. So without loss of generality, you can pass to a cover of S and just say it's a singleton. Now, so this Hodge index theorem part 2, the action on the tangent space is unitary. Observes a Kähler metric, and this has an integral structure. This implies it's finite. Now it's a fact from Riemannian geometry that if you have a isometry of a manifold which acts trivially on the tangent space at one point, it's actually trivial. Maybe I should stop there so we can get lunch.
Questions for the speaker?
So the problem with using Z inverted at finitely many primes is that it's not discrete.
That's right, yeah. Yeah, so you could try to, what you would need to win is to prove some kind of analog of theorem 1 with the theorem B here, part 1 with the p-adic topology here. And I think it's hard. So I can tell you there's some statement about harmonic maps to buildings that would imply it. I don't know if that statement is true.
Would it be easier to use additions instead of p-adic?
Say it again.
Would it be easier to use the additions?
I think it would be the same kind of concept. Somehow you need to understand something about the dynamics and on the p-adic points. I think we don't really understand that.
Yeah, so is that clear to say there's isomonodromy condition analog of the geometry?
Sorry, say it again.
Like this condition of being isomonodromy. And this should be an analog of the being geometry.
So I think being a family of flat bundles being isomonodromic is analogous to having a flat section to the Gauss-Manin. That's what you should think. So the isomonodromy foliation is the non-Abelian analog of the Gauss-Manin connection, and being isomonodromic means you're flat for the Gauss-Manin connection. I don't know if that answers your question.
You mentioned,
Is GNN by any?
Yeah, it should be fine with it.
mentioned there's some general terms from arithmetic dynamics. What are they?
Oh yeah, so I was claiming that if you have Yeah, so that you have a group action on a variety. You can bound the length of an orbit of an OK point, assuming it's finite, only in terms of OK. Like and that being variety. So you can't have Z points with bigger and bigger finite orbits. That follows from some p-adic interpolation in terms.
So I have a question.
Yeah.
So if I'm done correctly, you can prove a really strong theorem, namely that all your leaves are algebraic.
Yeah.
Is it possible to relax the hypothesis and talk about the algebraicity of certain leaves?
That's a great question. So I've written a paper on that topic, which is okay. So this paper is not yet out. Hopefully very soon. So my previous paper with Josh, we formulated a conjecture there and proved it in some cases. So the conjecture is the following. So you have a foliation. Suppose when you write down a formal leaf, only finite and many prime numbers appear in the denominators with structure constants of that leaf. So then the conjecture is that that specific leaf should be algebraic. And so we definitely can't prove that conjecture. I think if you could prove that for isomonodromy foliations, you would have resolved the full p-curvature conjecture. But we prove it for isomonodromy foliations at leaves passing through Gauss-Manin. That was sort of the main point of that. Yeah, so in some sense, I think of that paper as being about points, and this result as being about all of M-Rom, and then there's some interesting questions about motivic subvarieties of M-Rom. It would be nice, and it would be useful if one wants to attack the classical p-curvature conjecture.
Can you reformulate the conjecture, but just on in this situation, the geometric situation, not using M-Rom, but using a moduli?
I don't know. That's a good question. I think
Because,
so. Definitely, the isomonodromy foliation is not algebraic. Definitely, the isomonodromy foliation is not algebraic on M-Dolbeau. So it's hard. I mean, what?
I'm sorry. Why,
So
do you say it's not algebraic?
Yeah, so the isomonodromy foliation, I mean, you can sort of transport it to M-Dolbeau and get a real analytic foliation.
Sure.
But it will not be holomorphic or algebraic. So it seems challenging.
But it's not algebraic here, so
So the isomonodromy foliation on M-Rom is algebraic. I mean, the construction I gave was not algebraic. It's a theorem on M-Rom. It actually is algebraic. But
foliation.
yeah. The leaves are definitely not algebraic in general. The subsheaf of the tangent.
The subsheaf, yeah, of course.
Yeah, but that's not true on the Dolbeau side.
Yeah, but the leaves are not.
Right. Yeah.
Yeah, but I play exactly the orthogonal game, so to speak.
Okay.
So the sheaf is not algebraic, we agree. But yeah, that's a question about what corresponds to the leaves.
Yeah, so I mean, I sort of hit something in this theorem A prime. So there is some shadow of this story on the Dolbeau side. So on the Dolbeau side, you take the Hodge moduli space. So over one, the tangent exact sequence splits, right? That's the foliation. And then as you send lambda to 0, what you get is a splitting of the tangent exact sequence, except you go back then forward, it's multiplication by lambda. So when lambda is 0, you get a map from the tangent sheaf of S to the tangent sheaf of the fibers of the Dolbeau moduli space. So that's the sort of analog of the associated gradient of the Gauss-Manin connection. So I think that's the shadow of isomonodromy on the Dolbeau side. But I mean, that's what this theorem A prime is about, but I don't know how to formulate the full, I mean, somehow the vanishing of that thing is exactly the same as F isomonodromy preserving the Hodge filtration. So at least I guess this statement here, does F isomonodromy preserve the Hodge filtration? You can formulate on the Dolbeau side. So, but maybe that's as far as I know.
But let me insist a little bit. In the so-called Katz formula, which is still on the board, I think on the left part here, it is just describing this gradient associated to the p-curvature by what comes from the conjugate filtration. That's the main point.
Yeah. Oh yeah. So this theorem A prime is completely analogous. Oh yeah. Sorry.
Yeah. So the moment we talk on the conjugate filtration, this means that we think the analog in characteristic zero is precisely the Dolbeault moduli space.
Of the Hodge, the graded Hodge filtration,
Yeah, I mean, cut down to not Dolbeault, but we think of the we think of the Dolbeault object as this. It is not completely out of the blue that we have tried to generalize precisely here by saying something on the Dolbeault modular space.
So that's this term A prime I didn't write down. So what it says is that there's some kind of conjugate moduli stack, characteristic P, identification of its zero fiber with the zero fiber of the Hodge moduli stack, which is the Dolbeault moduli space up to Frobenius twist. And then there's two objects here. One is supposed to be the associated gradient of the p-curvature. One is supposed to be the associated gradient of the Gauss-Manin connection, and they so that's the statement of this theorem A prime, but it would take another 10 minutes to introduce the objects, but I can explain it to you after.
No, that I understand better. Yeah.
Yeah, so there is I think there is a good analog of this one.
I think there's no more questions, it's time banned for me.